This is the second part of problem solving on continuous functions on topological spaces. So our next question: prove that a point x is a limit point of a subset A of x if and only if A minus singleton x is a member of some filter converging to x. Now this is a 4 marks question. So first, let us let x be a limit point of A, which is a subset of x, where x tau is a topological space. Okay, now if nx be any neighborhood of x, this is a family of all neighborhoods of x, right? Scripted nx. So now we have to prove that A minus singleton x is a member of some filter converging to x. Okay, since this is a neighborhood and x is a limit point, so it proves that nx minus singleton x intersection A is non-empty, that is nx intersection A minus singleton x is non-empty. Okay, now let us take a family of sets G which contains sets G1 from X such that this intersection nx minus A singleton x is totally contained in G1. Okay, G is a filter, G is a family of subsets of X such that this intersection is contained in G1, that is G1. Okay, so this is easy to show that G is a filter because G does not contain phi. Okay, nx intersection A minus singleton x is never phi because x is a limit point of x is a limit point of A, so this is non-empty, so this cannot ever be phi. So phi does not belong to capital G, which is the first condition of the set G to be a filter. Now in the similar way you can check all the other conditions. So let's get to the proof. Let G be a filter. Okay, then G is a filter containing all such sets G1 which contains this set. Okay, now then for every nx belonging to nx, that means for every neighborhood, we can have nx intersection A minus singleton x is a subset of nx, right? Intersection of these two is subset of this one, so this is quite clear. And since this belongs to G, so the superset nx also belongs to G. Superset also belongs to G. Why we can say that this belongs to G? Because this set itself contains the set. This set contains itself, so this set satisfies this condition. So nx intersection A minus singleton x is itself a member of G. So this is quite understandable. Now since for every such nx, this nx belongs to G, that means the filter G converges to x. Okay, and also nx intersection A minus singleton x is a subset of A minus x, and G is a filter, so this set belongs to G means this set also belongs to G. So the first part is proved. Now the converse part, conversely, we let that G be a filter converging to X that contains A minus X, A minus singleton X. Okay. We assume that G be a filter that converges to X and also G minus X, A minus X is contained in G. Now we need to show that X is a limit point of A, of this set A. Since G converges to A, G converges to X, so for every neighborhood Nx of X, Nx is contained in G. This is what we mean when we say that a filter converges to a point. So now we have that Nx belongs to G and A minus singleton X belongs to G. So by definition of a filter, we have what? By definition of a filter G, we have that Nx intersection A minus singleton X also belongs to G. And since G does not contain phi, this means for any neighborhood we have this not equal to phi. And this shows that X is a limit point of A. Hence this is proved. Next question, which carries 2 marks, says give an example with reason of a topological space on which every real valued continuous function is constant. So the simplest example we can give is, let us take X is equal to singleton A. X is a singleton set, so it is non-empty for sure, and tau be discrete topology. Then tau consists of what? Phi and A, which is X itself. So this is the topology and this is our set. So any function defined on this set X must be constant. Why? Because there is a singleton. So f be any function from X to X, fx will have to be A for every X belongs to X, because there is only one X which is A in capital X. So this one is very much simple. Our next problem is define a net, and in a topological space X tau, prove that Sn such that n belongs to D is a net converging to U which belongs to X, capital X, if and only if there exists a filter in capital X which converges to U. This carries 5 marks. In the first part of continuous functions, I introduced the definition of net. So we will solve the second part. So let this be a net Sn such that n belongs to D greater or equal to, but this is a directed set, so this defines a net. Let this net converges to U belongs to X. Now we need to show that there exists a filter that also converges to U. Let us define a function. Let us define a set, family of set Sm such that M belongs to this directed set D and M greater or equal to N. Okay, so for every such N, An forms a set, and these Ans, for all values of N, there exists a filter. These Ans together forms a filter. Now since this net converges to U, So for every neighborhood NU of U, this net eventually belongs to this set NU, right? So there exists some n for which we can say that this AN and this AN belongs to NU. This AN is a subset of NU. Okay, this AN is a subset of NU. And since each AN is a member of this filter F, so NU being a superset of AN is also a member of F. So for any neighborhood NU of U, NU is a member of F. So all the neighborhoods, so the total neighborhood system of U is a subfamily of this filter F, which proves that this filter converges to U. Now, to prove the converse part, conversely let F be a filter, okay, which converges to U. Now we need to show that there exists some net which also converges to U. But before we find a net, we have to find a direct. So let us define a direct D by X, call it U, okay, X U. U is a subset such that X belongs to U and U be an element of a filter F that we already defined. Now we have to define a direct on the set D. So let us define this. Let this relation is defined on the set D when XU is greater or equal to XV if, no, to more generalize it, XU is greater or equal to YV if U contains V. So by this sign we are defining a direct on the set D, right? Now since we have already found a directed set D along with this sign, so we have to define a net on the directed set D. Okay, so let us define S from the directed set D greater or equal to X such that S of X U is equal to X. Since every element of D is of the form X U, where X belongs to this set U and U belongs to the filter F, right? So we have defined this net. Now the most important part is we have to show that for any neighborhood NU of U, we have to show that this net eventually is eventually in this neighborhood NU. Okay, so what does that mean? We have to show that S of some N, where N belongs to D, so N must be of the form XU. So we have to show that S of some N will belong to NU and there have to belong some M such that this relation holds whenever N greater or equal to M. Okay, so we have to show that there must be some M such that N for every N greater or equal to M from the directed set D, we can show that S of N belongs to NU. Okay, now since we know that every N from the set D is of the form U and M, where U belongs to M. Since U belongs to N, N becomes a neighborhood of U. Now let us say this is some NU and U belongs to this NU. Okay, now if for any n in which this NU is contained, that means what? N contains this NU. So we can say, by the definition of the relation greater or equal to, we can say UN is greater or equal to UNU, right? So we can say that for every UN there exists some UNU such that S of UN is equal to U by our definition of S. So it is equal to U, it belongs to NU whenever UN greater or equal to some UNU. So we have proved this one, right? We have proved this. This shows that this net converges to the point U. So our theorem is done.